Welcome to Mission for Excellence. Today we will do properties of Fourier transforms. Properties of Fourier transforms. So the first property is linearity property. First property is linearity property. Linearity property states that if you know the Fourier transform of two functions, then Fourier transform of their linear combination, that is C1fx f1x plus C2f2x, or you can take fx and gx here. So C1fx plus C2gx will be equal to C1 Fourier transform of fx plus C2 Fourier transform of gx. This is the linearity property. So let us prove it. By the main definition, Fourier transform of C1fx plus C2fgx will be equal to minus infinity to infinity C1fx plus C2gx into e raised to power minus iota sx dx. Now let us separate the two integrals. So we can write it as minus infinity to infinity C1 fx e raised to power minus iota sx dx plus minus infinity to infinity C2 gx e raised to power minus iota sx dx. Now we can take these constants outside. So it will become C1 integral minus infinity to infinity fx e raised to power minus iota sx dx plus C2 minus infinity to infinity gx e raised to power minus iota sx dx. Now we can write it as Fourier transform of fx because it is minus infinity to infinity fx e raised to power minus iota sx dx. From the basic definition of Fourier transform, we can write it as Fourier transform of the function fx. So we will take here C1 Fourier transform of fx, and similarly this we can write as Fourier transform of gx. So it will be C2 Fourier transform of gx. So hence the property is proved. So this is the linearity property. Now let us do another property that is known as change of scale property. This property states that if the Fourier transform of fx is denoted as f bar s, then the Fourier transform of f of ax, when x is multiplied by a, then Fourier transform of f of ax will be 1 by a f bar s by a. This is the change of scale property. So let us prove that. So by the definition of the Fourier transform, we have f bar s as minus infinity to infinity fx e raised to power minus iota sx dx. This is the Fourier transform of any function by the basic definition. So now let us take the Fourier transform of f of ax. So now the Fourier transform of f of ax will be, according to the same definition, it will be minus infinity to infinity f of ax e raised to power minus iota sx dx. Now to perform the integration, let us suppose this ax as t. Let this ax is supposed as t, then we get dx as dt by a. And also the limit, when x tends to infinity, t also tends to infinity, and when x tends to minus infinity, t also tend to minus infinity. So the limit will remain same. So now let us do the Fourier integration. F of f(ax), Fourier transform of function of ax, that is equal to, the limit will be same. F of ax means we have supposed ax as t, so we get here ft e raised to power minus iota s. Now x is t by a, so we write here t by a, and dx is also dt by a. So now this can be written as this 1 by a we can take outside. So this will be 1 by a minus infinity to infinity ft e raised to power minus iota s by a into t dt. So it means this is the Fourier transform of the function with the parameter s by a. So we can write it as 1 by a f bar s by a. Here the parameter, this s is replaced by s by a. So this is the change of scale property. So now we have studied two properties, linearity and change of scale property. These two properties are also applicable for Fourier sine transform and Fourier cosine transform also. In that case we will take here cos sx or sine sx as we need and prove as this. So this is the change of scale property. Now let us do the third property, that is known as shifting property. So it states that if f bar s is the Fourier transform of function fx, then e raised to power minus as f bar s will be the Fourier transform of the function f of x minus a. Means when you replace this x by x minus a, then its Fourier transform will be multiplied by e raised to power minus iota as. So let us prove it. So by the main definition, let us take this Fourier transform of function of x minus a. By the basic definition, this will be equal to minus infinity to infinity e raised to power minus iota sx f of x minus a dx. This is by the main definition. And now to perform the integration, let us suppose x minus a as t. X minus a as t. So dx will be equal to dt. Now the limit, when x tends to infinity, the t will also tend to infinity, and when x tends to minus infinity, t will also tend to minus infinity. So the limit will remain same. So now let us perform the integration. So this integration will now become integral minus infinity to infinity e raised to power minus iota. Now value of x from here is t plus a. So we put here t plus a. Now this will become ft and dx will be equal to dt. So now from this, if we take this function outside, e raised to power minus iota as. So let us first open the bracket. E raised to power minus iota st, e raised to power minus iota as, ft dt. Now since the integration is with respect to t, so the term of containing this s will be taken outside. So we take here e raised to power minus iota as, e raised to power minus infinity to infinity e raised to power minus iota st ft dt. And from the definition, it is the Fourier transform of the function ft. So we write it is f bar s. So it will become e raised to power minus iota as f bar s. So this is the shifting property. Next is very important property, that is known as modulation property. This property is very important for the examination point of view also. So the modulation property states that if f bar s is the Fourier transform of function fx, then Fourier transform of fx cos ax. Cos ax means this fx is multiplied by cos ax instead of e. So now the Fourier transform of fx cos ax will be given by this 1 by 2 f bar s minus a plus 1 by 2 f bar s plus c. Means it is the mean of the Fourier transform at s minus a and at s plus a. So this is the average value. So now let us prove it. So by the main definition, we take Fourier transform of this function. Fourier transform of fx cos ax will be equal to minus infinity to infinity fx cos ax e raised to power minus iota sx dx. Now as we all know the formula, e raised to power iota theta plus cos theta will be equal to e raised to power iota theta plus e raised to power minus iota theta divided by 2. This is the formula which we get from the complex. So we use this formula. So we will replace the value of cos ax by e raised to power iota ax plus e raised to power minus iota ax divided by 2. So now let us do this. So now this will become minus infinity to infinity fx e raised to power iota ax plus e raised to power minus iota ax divided by 2. This is the value of cos, and here we have e raised to power minus iota sx dx. So now let us combine these two terms and separate the integrals. So now we will get 1 by 2 minus infinity to infinity fx e raised to power minus iota s minus a x dx. This is the first, iota sx plus iota ex. So we take here minus common, plus the second integral will we take from this minus plus 1 by 2 minus infinity to infinity fx e raised to power minus iota s plus a x dx. So now this is the Fourier transform of the function fx with the parameter s plus a, and this is the Fourier transform of the function with parameter s minus a. So we will write here 1 by 2 f bar s minus a plus 1 by 2 f bar s plus a. So this is the modulation property, and this is very important property in case of Fourier transforms. Hope you like the video. So click on the bell icon so that you can get the notification about the next video.